Assalamu alaikum everyone. Have you ever opened your organic chemistry notes, looked at SN1 and SN2 reactions and felt completely lost? Like no matter how hard you try, the concepts just don't stay clear? Let me tell you something important today. Confusion is not a sign of weakness. It's a sign that you're about to understand something at a deeper level. Hi, I have been teaching O-level and A-level students for the past 5 years and I have seen one common thing. Students don't struggle because chemistry is difficult. They struggle because they haven't been shown the right way to think about it. In today's sessions, I am going to share a simple mentor secret that will help you never confuse SN1 and SN2 ever again by using logic, patterns, and exam-focused understanding. And if you really want to improve your grades and confidence in organic chemistry, I am excited to share that my new batch enrollment is now open, where I personally guide students step by step with concept clarity, practice questions, and exam techniques. So stay with me, keep your notebook ready, because today chemistry is going to start making sense. Okay, so before we jump into SN1 and SN2, we need to understand the foundation. What exactly is a nucleophilic substitution reaction? And trust me, once this becomes clear, half of your confusion will disappear automatically. So look at this definition on the slide. It might seem technical, but I'm going to make it very simple for you. So what do you know about nucleophilic substitution reaction? A nucleophilic substitution reaction is an organic reaction where an electron-rich species, the nucleophile, or attacks an electron-deficient electrophilic carbon atom to replace a living group. The nucleophile forms a new covalent bond while the living group departs with the pair of electrons. Think of it like this: one friend leaves the seat and another friend takes the place. That's it. That I have told you before, a nucleophilic substitution reaction is basically a replacement reaction. An electron-rich species, the species which has a lot of electrons, which we call the nucleophile. For example, you can see that carbon is containing partial positive sign. Why? Because carbon is right now electron deficient. Why? Because the electron pair is attracting by electronegative atom that is actually containing the partial negative sign. In the result, first of all, the carbocation formed is then how it will form. The most electronegative atom will leave from the carbon and making it positive one. Then the carbon positive containing positive charge formed is then liable to attack by nucleophiles. Why? Because now it wants to get stability. So anions are neutral molecules that possesses a lone pair of electrons. For example, now nucleophile will attack to stabilize the carbon atom and stabilize itself. By this way, one friend, as you can see that one atom left and nucleophile attack and attach to the carbon to just get stability. So often nucleophile will attack the carbocation carbon before the halide ion has left. We also have another possibility in which you can see that nucleophile attack first and then halide ion can left after the nucleophile attack. In both cases we will have a same product, as you can see, and the dominant reaction of halogenoalkanes is therefore nucleophilic substitution. Don't forget this point. Whenever we talk about the halogenoalkanes, then the dominant reaction will be the nucleophilic substitution. And the reaction can proceed in both ways. First, the halide ion can left, or either nucleophile can attack first. So don't forget that the product will be the same. Nucleophile will attach to the carbon atom to just stabilize its character and its position. Think of it like this: you have swapping a player on a football team. The old player leaves, a new player comes in, and the game continues smoothly. Let's see some other real life examples where you can see that halogenoalkane is reacting with OH negative and OH is reacting as a nucleophile because it is actually going to give the electrons to the carbocation, which will be deficient when halide ion will remove. So what will be the product? It will be methanol. making alcohol from halogenalkene. The second one, in which Cn negative is reacting and acting as a nucleophile, so Br will remove, making a nitrile. CH3CH2 with iodine is reacting with NH3, you can see that, and making an amine. What will happen? Amine will form and halide will leave as a living group. See how simple it becomes when you think of it as attack and replace. That's the secret to never confusing SN1 and SN2. Visualize the nucleophile as the attacker and the living group as the one being replaced. Every reaction tells a story. The clearer you see the story, the easier is it to master chemistry. Now let's dive into one of the most important reactions in organic chemistry, SN2 reaction. Don't worry, once you see it step by step, you'll never confuse it again. So first of all, let's discuss some of the important key concepts. What is SN2? Well, SN2 stands for substitution nucleophilic bimolecular. Let me break it down for you. It's fast. The reaction happens in one go. It's crowded. The nucleophile and substrate meet at the same time. It happens in one step, and the key feature is inversion of configuration. The nucleophile attacks from the back and pushes the living group away. So key concept to remember is strong nucleophiles don't wait, they attack immediately. Let's look at a classic example, the reaction of an alcohol with hydrogen bromide. As you can see that here what's happening, the hydroxyl group, that is OH, is protonated by HBr to become a better living group, that will be water. How? Because oxygen, as we know that we need a halide, okay, and OH is actually here the nucleophile. So OH negative will attract the proton that will be attached to the Br negative. What will happen? OH will react with hydrogen to make the water molecule. Now when Br will come, the bromide ion, what will happen then? The bromide ion attacks the carbon from the opposite side. Water leaves and we get ethyl bromide from the opposite side. Water leaves and we get ethyl bromide, all in one smooth step with inversion of configuration. In short, we can see that the hydroxyl group is protonated by HBr to become a better living group, that will be water. The bromide ion then will attack the carbon from the opposite side. Water will leave and we will get ethyl bromide in one smooth step. Now let's have a look on some strong nucleophile. As you can see that here, first of all we are having OH negative, that is actually making alcohols. With RO we can make ethers, with HS we can make thiols, with RS, R is representing here the carbon molecule, any carbon containing hydrogen molecule, any alkane you can say, will make sulfides. Cn negative will make nitriles, N3 negative will make azides, and Cl negative will make any halides, as we have discussed in our previous slide. Now that we understand SN2 reactions and how a nucleophile attacks the carbon, it's super important to know which nucleophiles are strong and fast enough to take change. So here's a quick table of strong nucleophiles that you should remember. OH negative is actually a strong base and reacts very fast. OR negative, that is actually alkoxide, very reactive. And if I talk about the Cn negative, then it makes nitriles, as you can see, and fast attacker. NH3 and the NH2. Let me make it clear for you, as I have not mentioned here the NH2 amines. Let me write it for you. NH2 amines and RNH2. Can anyone tell me what is the difference between the NH2 and the RNH2? NH2 is actually just a molecule and RNH2 is actually showing you the whole molecule, the complete one. R is actually presenting here the alkene group, as I have told you before. Now amines are actually the good nucleophiles. Now let me discuss the iodide and bromide. As we have seen in the previous slide that how iodine and how the halide ions are actually reacting as a living group. So you can also add them here. Br negative, okay. And thiols are also very strong. So strong nucleophiles don't wait, they attack immediately, just like you should attack your goals with focus and consistency. Now let's move towards the next slide. By now we have seen how SN2 reactions happen, how the strong nucleophiles are and why they attack so fast. Now let's bring everything together with a quick summary chart of SN2 reaction conditions. Carbocations are actually the carbon with one of any methyl or alkyl group and including 2 hydrogens. And if I talk about the secondary, then in secondary carbon will contain 2 of the any alkyl group like CH3, or it could be C2H5 containing 1 hydrogen. And if I talk about the tertiary, then what will happen in tertiary? Carbon will contain only the alkyl groups and there will be no hydrogen. So just remember it in a simple way that methyl is actually the carbon with 3 hydrogen, primary is actually carbon with only 2 hydrogens, and secondary is only 1 hydrogen. And secondary is the carbon which is actually including only one hydrogen in its molecular structure. In methyl you can see that the carbon is actually containing only the hydrogen atoms, so there is less hindrance, so it will allow easy backside attack. Nucleophile can attack very easily to the methyl, then to the primary, and then in the secondary. Why? Because due to the less stirring hindrance in methyl, because it is actually containing hydrogen only, which is actually a lighter group than methyl and the other alkyl groups. Okay, now let's move towards the second point, that is nucleophile. Strong and anionic and non-bulky will make a strong small nucleophile speed up the reaction rate. You should remember this point that when nucleophile is strong, anionic like any halide ion, and non-bulky, then a strong and small nucleophile speed ups the reaction rate. If you have the solvent polar aprotic or acetone like DMF and MECN like DMSO, for polar aprotic it does not solvate the nucleophile faster reaction and does not act as a nucleophile. If you are having any solvent that is polar aprotic, then it does not solvate the nucleophile faster reaction and does not act as a nucleophile. Living group, if you are having a good living group, then weaker bases make better living groups. And we also have to maintain the temperature if the reaction mixture is uh, going on low to moderate reaction, then high temperatures tend to favor elimination E2 reaction over substitution reaction. This is the very important point. If you are actually having any reaction and if you are observing that there is a very low temperature, and then you can say that it will be substitution reaction, because the high temperatures tend to favor elimination reaction. In this slide you can say that the substrate in primary reacts faster than the tertiary, and crowded SN2 slows down due to the steric hindrance that is actually creating due to the presence of a heavy group. If your nucleophile is strong, then OH negative attacking will make alcohol, and the solvent like CN negative will, and the Cl quickly forms the cyanides. As you can see that bromide leaves faster than fluoride, making CH3CH2Br more reactive than CH3CH2F. Now that we have mastered SN2, it's time to talk about SN1 reactions. And trust me, once you understand this, you'll never mix it up with SN2 again. Let's think of SN1 as a crowded elevator scenario. Imagine a busy elevator full of people. It's crowded, slow, and things don't happen all at once. That's exactly how SN1 works. It's a two-step reaction, unlike the fast one-step, SN2. Let's discuss its first step. The leaving group, that is actually bromide or any halide like bromide in a tertiary bromide, leaves first. The carbon becomes a carbocation, as you can see this. An empty spot in our crowded elevator. Now the nucleophile in this example, that will be water, enters and attaches to the carbocation, forming a new compound that will be alcohol, or it is propanol. Here is the reaction. You can see that the bromine leaves first, creating a tertiary carbocation, then water will attack and will form tertiary butyl alcohol. Now let's discuss some of the key points for the SN1. SN1 reactions love bulky molecules. Why? Because carbocations are stabilized by the inductive effect of three surrounded alkyl groups. More the alkyl groups, more will be the atom molecule heavier, and more the heavier of the molecule, or more the alkyl groups are present around around each carbon, it will make a stabilized carbocation. Unlike the one shot SN2, SN1 is a two-step process. Step 1 will be slow. The leaving group departs, leaving behind a carbocation intermediate. This is the bottleneck of the reaction. And in step 2, what will happen? That will be so fast. The nucleophile attacks the positively charged carbocation to form the final product. Let's dive deeper into SN1 reactions and understand why they love bulky molecules. Key concept: SN1 reactions love bulky molecules. Why? Because carbocations are stabilized by the inductive effect of three surrounded alkyl groups. Imagine the carbon like a VIP in a crowded room. The more friends alkyl groups supporting it, the more stable it becomes. Now, unlike the fast one-step SN2, SN1 is a two-step process. Step 1, that will be slow, the bottleneck. The leaving group departs first, forming a carbocation intermediate. This is the slowest step, the bottleneck, because forming a carbocation takes energy and time. Then there will be a second step that will be so fast. Once the carbocation is formed, the nucleophile quickly attacks the positively charged carbon to form the final product. Think of it like this. Step 1, leaving group walks out of the party slowly. Step 2, the nucleophile jumps in immediately to take its place. The other key concept will be the unimolecular nature. the 1 in SN1. 1 is actually representing its unimolecular nature. Rate determined step. This 1 stands for unimolecular, meaning the rate of the reaction depends only on the concentration of the substrate, the alkyl halide, not the nucleophile. Now let's move towards the other key concepts for the SN1 reaction. The unimolecular nature, the 1 in SN1 rate determined step. The 1 stands for unimolecular, meaning the rate of the reaction depends only on the concentration of the substrate, the alkyl halide, not the nucleophile. You can also keep the equation in your mind. Let me write it for you well. So you can see here the rate will be equals to this rate. The determining step will be equal to the concentration of the substrate and not the alkyl halide. Why? Because the nucleophile is waiting for the living group to depart on its own. Let me discuss some important point here. Patience is power, just like the nucleophile waits for the living group. In chemistry and in life, the first step often sets the pace for success. For example, you can see the example of reactions that we have discussed in our previous slides. Formation of the tertiary carbocation is the slow step. The rate depends only on the substrate. Water attacks quickly after that, and there will be no effect on the rate. If you want to fully master SN1, SN2 and all tricky organic reactions, my new batch for O-level and A-level student is now open, where I guide step by step with easy tricks, visualizations and exam shortcuts, so nothing ever confuses you again. So grab your notebook and let's see why the carbocation stability is the real game changer in the next slide. Now let's discuss the bulky rule, that is actually the preference is for tertiary and then secondary and then primary, because as we have discussed that the carbocation is stabilized by the inductive effect of the 3 surrounding alkyl groups, and these groups push electrons toward the positively charged carbocation, making it more stable. And if I talk about the solvent and nucleophile strength, then the solvent SN1 thrives in polar protic solvents, unlike the SN2 which were actually reacting in the aprotic solvents. So SN1 like polar protic solvents like water or alcohols. These solvents help stabilize the ions formed during the slow step. Nucleophile, since the nucleophile is not involved in the slow step, weak nucleophiles like or are perfectly fine for SN1. Why? Because as we know that the SN1 actually prefer the carbon atom that is actually containing the more alkyl group. Then, like as we have discussed in the previous slide, that it will be preferred tertiary first. Why? Because in tertiary molecules of carbon cation will be more stable due to the inductive effect of the 3 alkyl groups. So just like that, if there will be more hindrance, then only a weak nucleophile can approach or can go towards the hindered molecule. So that's why due to the hindrance, SN1 actually proceed with the weak nucleophiles. Now that we understand carbocation stability, let's see what make SN1 reactions thrive, and that brings us to solvents and nucleophiles. Solvent. For solvent, SN1 reactions love polar protic solvents like water or alcohols. Why? Because these solvents stabilize the ions formed during the slow step, the living group departure and carbocation formation. Think of it like a safety net. Solvent holds everything steady while the reaction progresses. Nucleophile. Here is the interesting part in SN1. The nucleophile is not involved in the slow step, so it does not need to be strong. Weak nucleophiles like water or alcohols are perfectly fine. They just wait patiently to attack the carbocation once it forms. Think of it like this. Step 1. The living group leaves and the carbocation sits on a comfy chair supported by the solvent. Step 2. The nucleophile comes in and forms the final product. For example, If you are having the tertiary uh, bromide and you are reacting the tertiary bromide with water, then tertiary alcohol will form and hydrogen bromide will leave. Water is both the solvent and the nucleophile. Bromide leaves slowly because state determining step carbocation will form. Water attracts tertiary butyl alcohol is formed. These two effects reinforce each other. The SN1 reaction is faster with tertiary halogen alkanes than with primary halogen alkanes, whereas the SN2 reaction is faster with primary halogen alkanes than with tertiary halogen alkanes. Overall, we expect primary halogen alkanes to react predominantly by the SN2 mechanism, tertiary halogen alkanes to react predominantly by the SN1 mechanism, and secondary by the SN1 mechanism, and secondary halogen alkanes to react by a mixture of the two. These two effects reinforce each other. The SN1 reaction is faster with tertiary halogen alkanes than with the primary halogen alkanes, whereas the SN2 reaction is faster with primary halogenal alkanes than with tertiary halogenal alkanes. Overall, we expect primary halogenal alkanes to react predominantly by the SN2 mechanism and tertiary halogenal alkanes to react predominantly by the SN1 mechanism, and secondary halogenal alkanes to react by a mixture of the two. So, are you ready to finally master SN1 and SN2 reactions without confusion? Let me tell you why my upcoming batch is perfect for you. Mechanism mastery will go step by step with arrow pushing for important reactions like hydrolysis, cyanide and ammonia attacks. You will not just memorize, you will truly understand how each electron moves. The decision tree. Stop wasting time deciding which mechanism to use. I'll teach you a foolproof 10-second method to choose between SN1 and SN2 even under exam pressure. Predictive chemistry and how solvent polarity and inductive effects dictate the final product and yield. You'll start predicting reactions confidently like a pro chemist. Practice, check and repeat. That's how mastery happens. Success in chemistry comes not from memorizing reaction but from understanding patterns and practicing smartly. So if you are in O-level or A-level student looking to turn confusion into clarity, this batch is made for you. I'll personally guide you step by step with tricks, visuals and shortcuts so you can ACE organic chemistry with confidence. Seats are limited, so make sure you enroll now and take your first step toward chemistry mastery. So, are you ready to take your chemistry skills to the next level and master CAIE exams with confidence? Here is why my upcoming batch is perfect for O-level and A-level students like you. Targeted 100% alignment with the latest Cambridge assessment. As I'll provide you targeted CAIE excellence, 100% alignment with the latest Cambridge assessment international education syllabus. Organic chemistry mastery, step-by-step arrow pushing mechanisms for SN1, SN2, E1 and E2 simplified for good. Topical past paper intensives, solve the last 15 years of P1, P2 and P4 questions with examiner level marking schemes. The scientific method approach, time management hacks, learn the exact shortcuts to solve complex stoichiometry and redox equations in under just 60 seconds. Personalized feedback, regular mock exams and detailed performance audits to identify the weak bonds and fix weak bonds in your knowledge. Remote learning flexibility, high definition live sessions with recorded backups and PDF cheat sheets for 24/7 revision. Alright everyone, that's a quick glimpse of what we will cover in my upcoming chemistry batch, from SN1 and SN2 mastery to exam focus strategies and time solving tricks for CAIE O-level and A-level students. If you're ready to boost your confidence, improve your grades and finally master chemistry, don't wait, enroll now. Here are the contact details. Remember, the best time to start mastering chemistry is now. Don't let confusion hold you back. Take action today. Thank you for watching and I'll see you in classroom. Happy learning and stay motivated. Bye bye.